Hello everybody, this is Rudra Pradhan here. Welcome to BMD lecture series, and that too we will continue with prescriptive analytics, and the coverage is on nonlinear programming. In fact, we have already discussed several problems dealing with both linear programming and nonlinear programming. In fact, in the last lectures we have already highlighted the detailed structure of nonlinear programming. So, that means whether to use linear programming or nonlinear programming, that typically depends upon the kind of data structure and the kind of business problem. So, having the data and the kind of business problem, so we will have a model which can be linear one or nonlinear one. If it is a linear one, then you can solve through linear programming problem, and if it is in nonlinear programming case, then we can solve through nonlinear programming problem. So, now the kind of structure which you have here is the NLP, nonlinear programming, and in the NLP we have a different kind of structures. The typical structure which you have highlighted is a optimization, that to optimizing objective functions without any constraints, and in the second case we have the optimizations with constraints, and then we have a single variable case, multivariable case, we have a equality constraints case, inequality constraints case, then again we have a single constant case, multiple constraints case. So, likewise we have highlighted the details about the particular structure, and then we have actually discussed what are the ways we can get the optimal results, that is the optimality solutions, and look for the values of the decision variable through which you can address the business problem as per the particular business requirement. And having the clue of the details about the NLP, so we like to go for some kind of problem structure and look for the kind of solution, and that means the structure through which you can get the optimal solution to address the business problem. So, now in the first hand, so far as nonlinear programming is concerned, so what we have already mentioned, objective function and then one or more constants may be linear and nonlinear, and sometimes depending upon the problem structures there is a difficulty to, or that means there is a complexity to have the solution, and where if the case is more number of variables and more number of constants, and then the constants is nonlinear in character, then the complexity will be start increasing. Then optimal solution here in the case of NLP, not necessarily a corner point, and we have a local optimization and global optimization, and starting point influences the kind of solution. That means there is a high chance that we have actually local optimization and global optimization in a particular process or business problem. And in the nonlinear programming structures, the typical structure will be like this, and here there is a kind of objective function. This is what the objective function, and the typical constants will like this. So, this is what the type of constant which is actually nonlinear one, and like linear programming, we look for the kind of feasible zones and the kind of corner points and look for the optimal solution. This is also the case of nonlinear programming, and again we have objective functions with the constants and look for the kind of solutions. In fact, most of the business problem means around 90% of situations we have both objective function and constant and look for the optimal solutions, and in a very rare situation you will have only objective function and no constants, but we have already highlighted the kind of optimality or the kind of optimal solution structure, whether it is a kind of objective function with constants or objective function without constant. So, that means technically we have we try to understand how is the case and then look for the kind of optimal solutions. So, now so this is another kind of structure through which you can actually analyze the particular structure, and that is how the kind of requirement. And in fact, these are the type of structures. So, where we have a constants, and then we look for the kind of solution. And what we have already discussed, that it is not the optimal kind of solution within a particular optimal solution corresponding to objective function and constraint. Since it is a kind of nonlinear constraint, so we will find there are lots of possible points through which you can actually look for the optimality. So, what we have highlighted the local optimum, which can be visible here, and then we can have the kind of global optimum. So, in this case, this is the kind of local optimum, and this is what the kind of global optimum. Obviously, since it is a dynamic kind of environment, so you will find there is lots of ups and downs. So we have actually multiple structure through which you look for the optimal solutions, right. So, this is how the typical case through which you can address, and then what we can do. So, we can actually So, this is how the typical examples, and let us assume that the type of business problem, the objective is to maximize profit, and here there are three kind of profit structure. So, that is with respect to the first ones, and this is the first one, this is the second one, and this is the third one, where M represents the medical patients admitted, S represents number of surgical patients admitted, and P is number of other type of patients admitted in the particular process, and then look for the kind of optimality. That means, typically this is a health analytics problem, and where the particular structure is to optimize the profit subject to certain number of constants, and the constants are here is like this. So, the typical constants will be follow like this. So, that means, so we have a three constants corresponding to three different profit structures. So, the first constant is with respect to this one. So, that means, the typical problem will be with respect to three variables, let us say x 1, x 2, x 3, and there are three constants, constants 1, constants 2, and constant 3. And accordingly, so these are all research availability, and these are the inputs to the particular constraints, and then we are looking for the kind of optimal solutions. So, now corresponding to these information, so let us see how is the kind of problem. So, that means, like linear programming problem. So, in the NLP we will also have the kind of transformation. So, having the information, so the first step of the process is to transfer the information into a model, and then look for the optimal solutions as per the particular business requirement or the kind of management requirement. So, having the kind of information, then the final model will be means NLP nonlinear programming model is like this. So, maximize profit. So, this is what the profit functions, and so this is actually cluster of three different situations, and then if you will simplify, and then that by default will come into a kind of nonlinear structure. So, this is how the typical business structure, and then when we analyze or process the particular profit structures as per the business requirement or the kind of business character. So, the ultimately the objective function will have is here is the kind of nonlinear one, and then we have a certain constant here. So, what we have already mentioned, there are three constants corresponding to this particular problem. So, that means, technically, so this is what the constant sides. So, 1 3 3. So, obviously, this is how the 1 3 3. So, the typical constants will be the m plus s plus p less than equal to 200, m plus 3 s plus p less than equal to 560, and likewise we have actually 5 different constants altogether. So, constant 1, constants 2, and constants 3. So, obviously, so this is constants 1, constants 2, constants 3, constants 4, and that is how the objective function to be optimized and with respect to all these 4 constants. and like the previous case. So, we have objective function. So, what will you do? The typical structure since it is actually 3 variable case. So, graphically a little bit complex to get the typical solution. So, if it is a 2 variable case, even the there is a question of nonlinearity, still we can look for the optimal solution, that too by a graphical methods, and when the particular model extends to multivariable case. So, like the linear programming case, we can use actually algebraic method through which you can look for the solution. And here in the case of 3 variables, you can go by algebraic structure, the way we have already highlighted, that is the calculus based mechanism through which you can look for the particular solution. Of course, the solver can help us to get the optimal results corresponding to the objective functions, that is the nonlinear in character and subject to all these constraints, and out of which few constraints are linear type and few constraints are nonlinear type. So, now what is the usual procedure is just if it is let us say case of 2 variable case. So, first you plot the kind of constraints into equality, then kind of draw the kind of indications and find out the feasible zones, find out the corner point, and put these corner points to the objective function and check where is the value of the objective function is the highest, and accordingly we can actually find out the optimality, and where the value of the objective function will be highest, and that by default that will be the optimal solutions, and then check what should be the values of the decision variable corresponding to that optimal value of the objective functions. And this is what actually usual structure of graphics or graphical methods, and in the case of algebraic method. So, you can simply actually just follow the procedures, and then subsequently move on till you reach the optimal structure, where you can get the optimal solution and the values of the decision variable as per this particular business requirement. Of course, solver is there to help us. For instance, let me take you to the solver case, where you can actually you can understand the particular situations. So, this is what actually the kind of like linear programming structures, which we can have here, the kind of what we can call as nonlinear structures. Let us say this is a problem here, and the problem is with respect to 2 variables, that is x 1 and x 2. So, that means typically the business is with respect to 2 variables, it is a 2 product case, and since the model actually nonlinear in character. So, the objective functions and the constants will be nonlinear in character, and in fact, in this case we have actually we have the 2 variable case, but the modeling structure is the nonlinear in character. So, that means this one is the objective function here, and the objective function, the structure of the objective function is here is like this. So, what will we do here? Let us say okay. So, what we can do here? So, we just specify what is the objective function. So, that means x 1 is the decision variable, x 2 is the decision variable, and the objective function is maximizing z equal to 2 x 1 plus 3 x 2 and subject to constants. So, that means in this problem constants are actually nonlinear in character, where objective function is linear in character, but in the real life scenario the objective function can be nonlinear in characters, which we have already highlighted in the last example. And so there is a case like objective function nonlinear in character, where the constants are linear in character, or objective function is the linear one, constants are kind of nonlinear one, and third option is both objective function and constants are nonlinear in character. So, whatever may be the scenario, we have to actually look for the kind of optimality and the optimal solution through which you can address the business problem. So, now here in this case, so the objective function is like this, and the constants will be there are typically actually 2 different constraints, and in fact corresponding to x 1 and x 2. So, if you go by x 1 and x 2 here, and x1 x2 here. So, okay, so we have actually a dot product and cross product. So, that means this is what x1 squares and this is what actually x2 squares and x2 squares, and then this is x1 x2 and this is x2 x1. So, these are the kind of that's called as what we can call as in analytics language, it's called as dot product and cross product, and sometimes in the business language we call as interactive effect, and here the first constant is with respect to x1 square, that means 1 into x1 square. So, that means x1 square, then again 1 into x2 square, that is x2 squares and less than equal to 20, and the second one is actually x1 and x2 is less than equal to 8. So, this is what the actually constants which are actually both are actually inequality type. Now, having the objective functions and having these two constants, so we look for the optimal solutions. So, that means technically what is the procedure here? Like the same procedure which we follow in the case of linear programming problem. So, go to the data analysis and then we choose the solver package, and here we have actually already the entry. This entry is meant for the kind of linear programming that we have solved in the case of integer programming and goal programming case. But here since it is a non-linear programming problem, so first of all you have to change the requirement, and so what will you do? First you put reset, and so that the typical structure will be removed. So, now we have to enter the existing structure, it is more or less actually same, and what will it do here? So, the typical requirement is here the objective function. So, the objective function structure will be here. Okay. So, this is what the objective function, and then the typical constants. So, that means okay. So, this is okay. So, this is what the objective functions, and then we have the kind of see these are the options here. So, that means typically if you look here, so this is the indication about the objective function like linear programming problem. So, we have a maximum, minimum, and the typical the kind of nature of the objective function. Since it is a maximization type, so we have already opted maximization type, and then this is the box for decision variable. So, that means typically so what will you do here? So, we can give the indication about the decision variable here. So, that means technically if you click here, so it will ask you to indicate the decision variables, and then so there is a kind of constraints. So, like the case of linear programming problem, so the constraints can be added. So, put put the case of add-ons, and okay. So, the add-ons will be coming like this. So, here the case is the that will be the first indication, and since it is a sign is less than type, so we can put less than type, and the constant is the maximum availability is the 20, and again, so this is the first constant indication, then again put add-on that is with respect to second constant. So, you put the second constant indications, and then put its limit, this is also less than type, and put its limit which is actually 8, and so okay. So, this is what the indication. So, put here 8. Okay. So, then now this structure is okay to process. So, that means we have given the indication about the objective function here. This is the objective function indication, this is the decision variable indications, and this is what the constants indication. And now here actually there is no typical difference in the compared to linear programming and non-linear programming, that to the use of solver package. So, here the indication. So, we have a simplex LP format, and we have actually NLP format. So, now what will you do? Since our requirement is in NLP format, so just you put non-linear indication. So, after that we just put okay. So, that means technically you ask the solver now to analyze the particular problems, and give the kind of optimal solution. So, now the moment you put the indication okay, So, the solution is already available here. So, okay, so now it is ready to operate. So, this is how you have to give the indication. So, that means, so now, so the operation is here. So, this is what the indication. So, that means technically, so this problem and the corresponding problem is like this, and still we can apply actually sensitivity analysis and the kind of requirement, that means you can put the restriction what kind of the decision variables, whether you need actually in a kind of positive means non-negativity constants, and against like we have discussed about the kind of integer type of solution, etc. You can put all these conditions again in the solver to have the final outcome. So, then what will you do ultimately? So, in this case corresponding to this objective function and constants. So, we have x 1 equal to 2 and x 2 equal to 4, and where z equal to actually coming 16. So, that means, this is what the final outcome. So, it is actually the process is more or less same like linear programming problems. So, where we have already solved couple of examples through this particular solver mechanism, and here also same mechanism, just the typical difference is just you have to create a decision variables as per the particular requirement. So, so what will you do in the particular process? So, you have to first formulate the problem, and the typical structure is actually in the solver. So, the first requirement is how many variables altogether, starting with let us say for these two variable x 1 and x 2, then the next nonlinearity will come x 1 square, x 2 square, x 1 and x 2. So, these are possible kind of structures. So, then after knowing all these variables indication, then you start entering the objective functions and the kind of constants and the kind of requirement. Then after that just like linear programming structures. So, you just ask the solver to give the optimality result, and by default you will get the optimal results, and that too values of the decision variable corresponding to the particular objective functions and the kind of constant. Again, if you like to change the particular structure, which is the kind of application of sensitivity analysis. So, here we can actually change the coefficient of the constants left hand side, right hand side, change the coefficients of the objective functions. You can add one after another constant, and then again you look for the optimal solution. So, that means like linear programming problems, we have also here flexibility to find out the optimal solution corresponding to the original problem, and look for the further optimal solution corresponding to the changing scenario, that too with respect to objective function coefficients, with respect to constants coefficient left hand side and right hand side, and then we may actually look for the optimal solution against by including one after another constant into the system. So, then that means technically we have lots of flexibility here, like the linear programming case, and the dynamics of the business. We cannot just artificially or arbitrarily can add-ons variables or add-ons constant. Obviously, it should be supported by the particular business problems and the kind of theory. So, so either it will be supported by business problems or the kind of theory, or else if you like to add up add-ons any extra. So, it should be logically connected, so that you can address the particular business problem more accurately and more effectively, and then come with a kind of management decisions, and that too as per the particular business requirement. So, having a the kind of structure here. So, go back coming back to the particular problem. So, so now corresponding to this problem. So, we have the solution again here. So, the way we have already solved. So, this is also same case. So, we have a 3 variable case, but the problem which we have solved is a 2 variable case. So, here there are 3 variable case, and the 3 variables are M, S, P, and then corresponding to the kind of dot product and cross product and the kind of problem. So, we have here a dot product case, dot product case, dot product case, and this is a cross product and cross product. So, now so we what I have already mentioned, we cannot just mathematically connect, but all these inputs or the kind of problem formulation in the solver depends upon the existing business structure or business condition. Then actually we put the inputs and then look for the optimal solutions, and the optimal solution which will be received through the solver exclusively well connected with the original problem or the typical business problem. So, so in the first end we are not actually changing anything else. Depending upon the problem, we are just allowing the solver to have the optimal solution as per the particular business requirement. And then if any change we need need to apply, then again we can change the particular requirement and look for further optimality structure, and then we can compare so the existing optimal solution and the change optimal solutions. So, likewise so the process which you have highlighted in the Excel sheet. So, this is also same case. So, now in this case corresponding to this business problem. So, that means the typical business problem is here. Now, corresponding to this business problem. So, we have the kind of structure like this. This is how the input to this solver, and then in the next process we will have a solution. So, that means the solution is here. So, this is what the solution to this particular so this is what the value of the objective function, and again so we are looking for the values of the decision variables. So, the values of the decision variable is actually reported here corresponding to the objective. That means the objective function actually here is let us see here. So, this is what actually so m square s squares ms p and p square. So, that means we have a couple of decision variables. So, as a result, so we will find so these are the values of the decision variables, and as a result if you put all these decision variables values of the decision variable to the objective function, the objective function will give you the optimum value. And so that means technically this is the values of the decision variables, and this is what the value of the objective functions. That means technically if you look into the solver, so the solution mechanism is more or less same. So, it is actually the kind of objective function and the constant. Only difference is actually the kind of functional form only. So, earlier we have solved actually all the objective function and constants which are linear one, but here we are solving the similar kind of problem where either the objective function or the constants or both objective function and constants are nonlinear in characters. Then we are looking for the optimal solution. That means technically there is these are all not highly distant. Of course, mathematically we have actually described different kind of structures to look for the optimality and to have the optimality. But if you apply this particular softwares, then by default the process is more or less same, and depending upon the kind of problem requirement or the kind of problem inputs, so the output will be also getting accordingly. So, this is how the kind of solution corresponding to this particular problem. And now, so what I can say that this is what we have already highlighted, how we can obtain these results from the solver. So, now any change you will do, so the result will also change. So, we have actually a similar kind of structure. So, that means technically what I like to say is if I like to summarize. So, we have actually the kind of problems where we have objective functions, we have a constants, we have a conditions, and then the typical difference corresponding to the earlier discussion about the linear programming is that the either the objective functions or constants or both, they are somehow connected with the nonlinearity, and then we are looking for the kind of solutions. So, what I have already mentioned that there is a kind of local maximum or local minimum. In fact, what we have already solved through the kind of simplex structure or dual simplex structure. So, it is a iterative process. We will find actually a different kind of solution in every stage. The value of the objective function will be changing, and there is a kind of improved. So, that is why in every after every iterations we call as it is a improved basic feasible solution, and then finally we will stop where the particular value will satisfy the condition and constants, and then the value of the objective function is at the highest level. So, this is how the kind of structures, and usually, so if you look for the graphical structures where we have actually the kind of cost structure like this. So minimum means so we look for the particular structure like this. So that means what we have already discussed, the graphical structure, this is what the minimum point which you are looking. So that's why we are actually differentiating the total cost function with respect to the output, and by using the first order condition and second order conditions, then we can find out the optimal output where cost can be minimized. So that means that is how the, so that means if you look there are various options which you have actually before the point, before the optimal point and after the optimal point. So that is how actually the kind of structure. So that means typically here we have lots of flexibility options, like different corner points we have in the case of linear programming. We have also here different kind of options, but ultimately so there will be one corner point which can give you the kind of optimal solutions. So this is the case of a particular objective functions, and corresponding to this objective function, this is how the local minimum, and in the case of local maximum, it is just opposite. So it is a game between actually convex to concave only. So in the convex kind of scenario, so we like to go for local minimum, and in the case of convex type of situation, we look for local maximum. For instance, the typical structure which we will receive through the calculus based method, and that is how we have already discussed that first derivative should be equal to 0 to get this point, and second order sufficient condition will be just to support the particular process. That means it will just validate the particular optimality and the values of the decision variables through which you can address the particular business problem. And likewise we have actually here the case about the complex process, where we have 3 different points through which you can actually find out the kind of optimal solution. So that means technically if you go back to the previous structures, you will find there are there is only one single point which gives the kind of optimality structure. But now if you will come here, you will find there are actually 3 different points where we can have actually the optimality structure. So that means this gives the kind of indication or signal that there is the importance of robustness check. That is what the second order sufficient condition is all about, and this will give you the indication that out of these 3 different options, which one is the finally the best options to have the optimal results and to address the business problem as per the particular requirement. Okay, so that means we like to highlight the here the importance of the second order sufficient condition about the optimality requirement, right. So now corresponding to this A, so what will we have here? Here is the kind of structure called as constraint, and this is what the kind of profit functions, and then constraint will help you to streamline the process and then take you to the kind of optimality structures where it will satisfy the kind of requirement of the objective functions, and that too with respect to the conditions and the kind of requirement. And this is how the the one way to solve the problem through solver package again. So there is we have already solved. So this is how the typical case, again this is another kind of non-linearity. That means technically if you look for the various models, so in the case of non-linearity we have a more flexibility and more complex, and in fact it is more interesting than the kind of linear one. In the case of linear ones, so you will find one kind of indications either downward or upwards. It just changes the angles from one point to another point, but here this situation is more flexible in nature, where you will find in a particular situation there are options of ups and downs, and you will find more than one point where you can get the, it means we can have the kind of optimality, but ultimately the final optimality will be single one through which you can address the business problem as per the requirement. So this is what the feasible regions, and that means technically corresponding to the objective functions we cannot specify the feasible region until unless we can connect with the constraints. So now with a constraint, so we can actually have the feasible regions, then we look for the kind of solutions, right. This is another case. So, again solver can be helped to get the particular results. These are all solver outputs, and okay. So, so altogether what I have mentioned that the in the kind of prescriptive analytics, we have discussed several problems, the kind of linear programming structure, nonlinear programming structures, where we have objective functions, we have a constants, we have a conditions, we have a kind of restrictions, the kind of requirements, like integer type, and the kind of pure integer, mixed integer. So, means what I can say that we have a plenty of options or different tools in the kind of prescriptive analytic structure, through which you can address the business problem more effectively, more accurately as per the particular requirement. So, that means technically what kind of model we can use to address the business problem exclusively depends upon the data structure and the kind of types of problem, and the history behind the problems, some kind of extra innovative thought process you can add depending upon the particular requirements and dynamics of the business. Of course, these are all supported should be supported logically, but ultimately we need to find out the optimal solutions and the values of the decision variable, through which you can address the business problem more effectively, more accurately, and as per the particular business requirement. And that is what the beauty of the prescriptive analytics compared to descriptive analytics, inferential analytics, and predictive analytics. And this is something special case where we like to find out a particular position through which you can say that business is more effective and business is actually more efficient. So, that is the point actually means that is the point through which you can take the management decisions, or you can apply the management decision very effectively, and prescriptive analytics will help you a lot to come to the kind of situation and to address the problem as per the particular requirement. And with this we will stop here. Thank you very much. Have a nice day.